Next, we're going to do some examples of the chain rule. Now, because of the way I introduced the derivative rules, we've seen examples like this before. However, we're going to point out how the chain rule applies to these sorts of examples. So the first example is an interesting one, and that is compute the derivative of the function f of x is equal to sine squared of x plus cosine squared of x. So here we have to use the chain rule twice, once for each term in this function. Now the reason we need to use the chain rule is because we have a composite function. The inside function is sine of x, and the outside function would be u of x squared, so u squared. Because sine of x is really just something squared. So we have to think of sine of x as it being in a box, and we have box squared. The 2 comes down, we get 2 box to the 1, and then we multiply by the derivative of the inside. So we can rewrite this as sine of x squared plus cosine of x squared. Now the inside function, as I mentioned earlier, is right here, and it's more apparent that sine of x is the inside function. And then for the second term, the inside function would be cosine of x. We'll have separate work for each term, so I'm just going to use u and u, but they're separate u's. So just think about one u over here, another u over here. So here we have u of x squared. So when we take the derivative, what we do, the 2 comes down, right, because it's u of x squared, so it's 2 u of x to the 1, 2 times sine of x to the first times the derivative of the inside. So the derivative of sine is cosine of x. Then for the second term, we do the same thing. So cosine of x quantity squared, the 2 comes down, so we get 2 times cosine of x to the first times the derivative of cosine, which is negative sine. And I'm going to promote the minus sign to the front, so it's minus 2 cosine x sine of x. Hence 2 sine x cosine x minus 2 cosine of x sine of x. Now these two terms are the same, except one has a negative sign, which means they cancel out and we just get 0. Now you might have expected that if you picked up on the fact that sine squared of x plus cosine squared of x is always equal to 1. But what we actually did in this example is we proved the identity that sine squared x plus cosine squared x is equal to 1. The reason we proved that, well, we almost proved it. So what this proves, so I should start this as f prime of x, because otherwise the equality sign continues from the previous line, and f of x is not equal to this. This is f prime of x. So I start a new equation right here with f prime of x. So I don't want to link the derivative to the original. So the derivative is equal to 0, which means that f of x must be a constant function, right? Because only constant functions have a derivative equal to 0. So what we proved was that sine squared of x plus cosine squared of x is equal to some constant. Now to figure out what that constant is, we just have to evaluate that at one point. And let's pick an easy point. How about x is equal to 0? So f of 0 is sine of 0 squared, sine squared of 0, plus cosine squared of 0. Well, sine of 0 is 0, cosine of 0 is 1, so f of 0 is equal to 1. Since f of x is constant, that proves that sine squared plus cosine squared must always equal to 1. So that's a nice calculus-based proof of this trigonometric identity that you know very well by now. The second example, we have f of x is equal to 1 over square root e to the x plus sine of x. And so again, we have something raised to the power. So this is another, basically an example of the power down rule. But remember, the power down rule stems from the chain rule. And I'm going to go into a little bit more detail of how the notation of the chain rule can be applied here. So this is basically e to the x plus sine of x to the 1/2. Now, this f of x is really v of u of x. So we can write this as f of x is equal to v of u of x. So the u of x is the inside function, and the v of x is the outer function, or the outside function. So we have an inside function and an outside function. Now the inside function is going to be this function right here, because it's this and then raised to the 1/2. So we identify u of x as e to the x plus sine of x. And then v of u is going to be u to the 1/2. So you see what happens, or you can even say v of x is equal to x to the 1/2, because the function is the rule. The function really doesn't care what the name of the variable is. But to be consistent with over here, let's say v of u is the function u to the 1/2. So the function v just says I'm going to take the square root of whatever is coming in. And what's coming in isn't just a variable, it's u of x. So v of u of x, the composite function, is I substitute in e to the x plus sine of x where I see u. So it's e to the x plus sine of x raised to the 1/2. Now you know, because we've done these examples before, that to take the derivative, the 1/2 comes down, we get 1/2 this to the minus 1/2 multiplied by the derivative of the inside. But let's take a look at the specific construction with the chain rule. So the chain rule tells me that f prime of x is equal to v prime of u of x. So it's a derivative of the outer function evaluated at u of x times the derivative of the inner function, so times u prime of x. And you can think of this as just dv du times du dx, right? Because the derivative of v, you're taking the derivative of v with respect to its primary variable, which is u, times the derivative of u with respect to x. So v prime, so the function v is just u to the 1/2. So the derivative of that, so v prime of u is just going to equal 1/2 u to the minus 1/2, which is the same as 1 over 2 square root of u. We've seen that many times before. So therefore, f prime of x is v prime of u of x. So it's going to be 1 over 2 square root, and where I see the u, I replace it with u of x, e to the x plus sine of x. And then I multiply by the derivative of u of x. Well, the derivative of u of x is e to the x plus cosine of x. So altogether, f prime of x is going to equal e to the x plus cosine of x divided by 2 square root e to the x plus sine of x. So that is the function and how the chain rule is used. So this gives you a little bit more of the, we've been able to calculate these sorts of things before, but this shows you how it works in conjunction with the chain rule, right? So how this formulaically works with v prime of u of x and u prime of x. So let's do another example. So f of x is equal to secant of the ln of x. And so here, the inner function is clearly ln of x, inner function, and the outer function is the secant function. So basically v of u is equal to secant of u, and then u of x is equal to ln of x. Right. So you can see if we do and the function f is just v composed with u. Right. So it's v of u of x. So we take u of x and input it into the function v, right? Because v composed with u, which is a function of x, is v acting on u of x. So v, u of x, plug it into the u up here, we get secant, and then u of x is ln of x. So v of u of x is secant of ln of x, so it's that composite function. So again, the chain rule says that f prime of x is equal to v prime evaluated at u of x times u prime of x. So the derivative of the function v, so v prime of u, well, the derivative of secant is secant tan. So it's secant of u tangent of u. So that's v prime of u. And then u prime of x, derivative of ln of x is just 1 over x, 1 over x. So the chain rule tells me that the derivative of f of x being the composite function v composed with u, which is the function secant of ln of x. So the derivative of secant of ln of x is equal to v prime, which is secant u tan u, but evaluated at u of x. So that's going to be secant u of x was ln of x, tangent evaluated at ln of x, and then times u prime of x, which was 1 over x. So the derivative of secant of ln of x is going to be secant ln of x tangent ln of x times 1 over x. So this is basically the derivative with respect to the inside function times the derivative of the inside function with respect to x. And then let's do one more example. Example number 4, f of x is equal to ln of sine of x. So here the inside function again is the one on the inside, so the inside function is the sine function, and then the outside function is the ln function. So u of x, the inside function is just sine of x, and then v of u is ln of u. Now we know the derivatives of both of these. V prime of u is just going to be 1 over u, and u prime of x is just going to be cosine of x. So the chain rule says f prime of x is equal to v prime evaluated at u of x times u prime of x. So v prime is 1 over u, but we're evaluating that at u of x, so it's 1 over sine of x. And then we're multiplying by u prime of x, which is cosine of x. Cosine over sine is cotangent of x. So we just showed that the derivative of ln of sine of x is equal to cotangent of x. So those are a couple basic examples of using the chain rule.